So now a very important interview question that is asked from people is that you perform these traversals to me without the use of recursion. So let us start with the simplest one. You perform pre-order traversal for me without recursion. So guys, what do you think? If a code is recursive and you have to make it iterative, what will you use to make it iterative? Stack. Why stack? Because internally recursion also uses stack. So if you're not using recursion, you create your own stack and do whatever recursion was doing in its stack. So if you do something like that, then your job would be done. So how many of you can figure this thing out, that how can I use stack to get my job done? Okay, here I'm going to talk about the most important approach, and you have to be very focused while listening to me here, because this approach that I'm going to tell you now is a generic approach. It will apply in Preorder also, Inorder also, Postorder also. If you understand it here in these 5 minutes right now, you can use it for any kind of traversal without using recursion. Okay, and that's a very easy approach, the easiest form of code that you can write to perform iterative version of any of these 3 traversals. So there is one thing that we all should understand. Everything happens via recursion in these traversals if you write a recursive code, right? So first you make a call for your root. Let's say your root is 1. Okay, so you make a call. After making the call, what is it that you do? First you print this 1, and then you make a call for f of 5, and then you make a call for f of 6. Cool. So this was a constant time operation, so it got done, and now you are totally worry free about this one, right? Now how will your recursion stack look like? Will somebody tell me? I mean, will it look like this, or will it look like this? 1 or 2? What do you feel? Will it have f1 and f5 in it, or will it have f1 and f6 in it? It will have f1 and f5, right? That's guaranteed, because this call is still not made, right? This call is still not made, right? Because this call is still not made, the program has not even touched it. If the program has not even touched it, how can it put it in the recursion stack? It cannot do that, right? So what would happen is that after this call has been made. Now, the benefit of the recursion is this only, that because this function has not completely terminated, because this part of this function is not over, so by the time this is over, control will come here and then this call will get made, right? That is the beauty of recursion, right? Now if you try to understand this thing, if you are trying hard to do pre-order traversal in an iterative manner, so let's say you start from root, and then you print the root, which is you print 1, and then you move to root left. So now you come here. Now you will never be able to come back to here. Never be able to come back to here, because now you came from here to here, you cannot go up. And if you can't go up, how can you go in that right subtree, which is linked to this only, right? This is the problem. So stack is there to remember the parent, okay? To remember the parent. In other words, I can say it is there to remember this subtree, because if in my recursion stack I somewhere put this thing that, hey, once this is done, you please start your journey from here, then my job would get done. So the point is that whenever you touch a node in pre-order traversal, let's say you're starting from root, so whenever you touch your node, which currently is your root, you print it. And after printing it, what you do is you need both these nodes to be there somewhere in the stack, and it should be such that first f5, everything that is rooted at 5 should get printed, and then everything rooted at 6 should get printed. So this 5 thing should be there above this 6 thing in your stack. So this is the basic idea. Okay, now how to execute it, that we'll see later. So what I can do is that just tell me one very simple thing. Whenever your code touches a node, there are 2 things that it does. In any of these 3 traversals, I'm not talking about just pre-order, I'm trying to be generic. First thing that it does is it pushes its children, and once it has pushed its children, then next time, whenever it sees that node again, it can actually print it and get rid of it. I repeat it. If your code has already pushed the children in the appropriate order, then the next time whenever it sees that children again, because recursion comes back, right? So the next time whenever it sees that, not children, whenever it sees that root which had already pushed its children, it can actually print it and get rid of it, right? But if there is a root whose children are still not pushed, then the first thing that you need to ensure is that the children get pushed. Only when the children get pushed, then you are free to print that node out. So I have to somehow disambiguate between these things that, hey, given a node, whether its children have been pushed or not. Okay, so can somebody suggest me a way to do that? How do I check, given a node, whether its children has been pushed or not? You can think of it in this way. The first time you see a node, you push its children in the right manner, and then the next time you see that node, you simply print it out and pop it off from the stack. How I can do that? I can do that, have a pair, right? Along with the node, you also have a flag, and that flag will either be 0 or 1. If it is 0, that means you are seeing this node for the first time, so you'll just push the children, and if it is 1, that means children are pushed, so you'll just print it. So now we'll all see a very easy dry run of it. So let's say this was my tree. This was your tree, so you'll start your journey from the root. So first you will push this root, and when you push this root, you also have a flag with it. So that flag is 0. That flag is 0 because you have not pushed its children. Now, you always work with the top of the stack, okay? The top of the stack is 1, 0. So you will take it out. So you take it out. Once you have taken it out, you see that the flag is 0. If the flag is 0, it means that the children are not pushed. If the children are not pushed, it is your responsibility to push them, right? And now can you tell me, will you push right child first or will you push left child first? Right or left? Which should be pushed first into the stack? Right child, correct? Because I want this thing to get taken care of before this thing, and it would only happen if this thing lies on top of the stack. And for this to lie on the top of the stack, this should be pushed at the last and this should be pushed at the first, because stack is last in, first out. So now what you will do is you will push this child, right child, and then you will push this left child. Okay, and what will be the flags for them? What will be the flags for them? Whenever you are pushing for the first time, that means you have to put the flags as 0, 0 each. Yeah, so there will be 0, 0 each. And now you will push this back. Okay, now when you push this back, because you are pushing it back consciously after pushing its children, you have to put this flag as 1. Okay, again you will get to know the top of the stack. What will be the top of the stack? 1. So take it out. When you take it out, you see that its flag is 1. If its flag is 1, that means children are already there. So just print it and get rid of it. That's it. So this was my first iteration. Now again in the next iteration, what would happen? Again you would seek the top of the stack. The top of the stack is 2, 0. So whatever is the top of the stack, first take it out. Take it out. Okay. So if it has a flag of 0, that means its children are not there. If its children are not there, put them in the proper order. First right child and then left child. So whenever something is being pushed for the first time, this should be pushed with 0, 0. And now you have pushed its children, so now put it back again in the stack with 1. Again seek the top of the stack, that is 2, 1. So take this 2, 1 out. This is gone from here. And now since this flag is 1, so all its children would definitely be there. So just simply print it and get rid of it. Now again seek the top of the stack. The top of the stack is 3, 0. Take it out. 3, 0 is the top of the stack. Does it have a left child? No. So if a child is not there, you don't push it. Similarly, does it have a right child? No. So you don't push it. And then you push it back again with flag 1. So whenever you have inspected the children, you can push it back with the flag 1. Again you seek the top of the stack. It was 3, 1. So 3, 1 is out, the flag is 1, so you simply print it. What happens whenever the flag is 1, you simply print it and get rid of it. And whenever the flag is not 1, let's say you took it out and the flag is not 1, the first thing that you do is you first check if the right child exists, push it. If the left child exists, push it with the flag 0, and then you push this back with flag 1. And then again you seek It is 4 1, so you print this 4. This is how, it will go on. And now, when this 1 along with its left subtree is printed, I have this 5, so I can venture on this right subtree. So this is the benefit of it. Whenever you see a node for the first time, you don't just move on to its left child, you also move on to its right child. To do that, you put right child below the left child with appropriate flags. And this is how this would go on and on and on. So this is a very, very simple approach with which you can get your job done. Now, if somebody asks me to implement it, I need a stack, and that stack will be a stack of pairs. So let's say this is my stack of 2 things, node star, and the second thing is, let's say, int. It can be bool also, int, which is 0 1, right? And this is my stack. Now the first thing that you do is, in this stack you push a pair of root comma 0. And then how long will you keep working on this stack? How long the recursion keeps on working? As long as the stack is not empty, the recursion keeps on working, right? Similarly, as long as this stack is not empty, you would keep on working. So my termination condition would be while my stack is not empty, not of stack dot empty, you'd keep doing something. What is the first thing that you will do? Whatever is the top, take it out. So to take it out, you will do stack dot top. From this you will get a pair p, okay, and then you will do stack dot pop. So you have that value and you also have popped it. Now what is the first thing that you do? When will you simply want to print it and let go of it? If you see that the flag is 1, that means the children were already pushed. And if the children were already pushed, why not simply print it and move ahead? Yeah, so that should be the first simple logic that I should write. Okay, so whenever you are coding, first always write simple logics. Okay, that makes it better for you to keep moving on, right? So if you see that pair dot second is 1, that means children were already there. So in this case, all that I'll do is I'll print out the value of this node, and then that would be present in p dot first. That would be a pointer, so whatever is the value of that. That's it. This is all that I have to do if the top of the stack had a flag as 1. Now if that is not the case, then what do you feel should I do? Push children, right? But should you push children blindly? Should you do that? If you push them blindly, you would end up pushing and printing nulls also. So you have to check if the right child is not null, then you will push it. Similarly, then you will check if the left child is not null, then you will push it with the flag 0 0 each. And first you will push the right child and then only you will push the left child. Only then you will maintain the order of root, then left, then right. So first you will do the job for the right child. So if you see that p dot first is your node, so if the right of this exists, what will you do? So if the right of this exists, you would first want to push it. Okay, so how do you push it? You will do stack dot push, and yeah, so p dot first arrow right, and the flag for that will be 0, right? This is what you do when you see that the right child is not null. Similarly, the same kind of thing has to be done for the left child also, right? So you will check if the left child is not null. So if you see that if p dot first arrow left, if the left child exists, push that also in the stack dot push p dot first arrow left comma 0. You know why this is 0, right? Because they are being pushed for the first time. Because you're coming from top to bottom while doing recursion, you're pushing something for the first time, it should be 0. And then there is one last thing also that you should do. What is that last thing? You should push back this root as well, correct? And now when you push back this root, what will the flag be? The flag will be 1, correct? Why? Because the children are already pushed. So now you will do stack dot push whatever you had popped, which was p dot first, and now this will be 1. Yes, this is how it will go on, and this is the way you will get your job done. So if you get this correctly, can you comment on the time complexity? What is the time complexity here? Yes, why 2n? Because the maximum number of times my algorithm is touching any node is 2. Any node is either getting pushed first or getting popped after it was pushed initially. So 2 touches for every node, so it will be 2 into n, right? And what will be the extra space? Do you see extra space would also be order of n? It's just like recursion stack space, right? Yes or no? Because let's say this tree was very, very deep. Let's say when you are trying to print this thing, what would have happened? This 5 would be waiting for you. This 4 would be waiting for you because you have printed this 1, so this 5 was waiting. You have printed this 2, so this 4 was waiting. Similarly, once you have printed this 3, and let's say it had a right child again, 9, it also had 9, it also had 9. So all of these would be waiting for you. So whenever you are printing, let's say nth level, which is or hth level, where h is the height, if you are printing a node of hth level, for all the above levels, it would happen that these nodes would be printed, but their right children would be there in the stack, so that once this is printed, then you start printing this, and then you come to this, and then you come to this, and then so on and on and on. So here also it will be order of the height. Now, if you learned this approach for pre-order, don't you think you can do it for in-order also? Everything is going to still remain the same. You start your journey with the root, okay? You start your journey with the root, let's say it was 1, 0. And first you bring it out. Whatever is the top, just blindly bring it out first. And if you see this is 0, what would you want to do? Would you want to let go of it here itself? No, because the children are not there. So you'd want to push the children. But in what order will you push the children? Tell me that. Definitely, first you would want the right subtree to be printed, and then you would want the left subtree to be printed. But between your printing of right and left, this root should come, correct? So what should be my order? Yeah, first you would push the right node, and then you would push this root node, and then you would push that left node. Simple enough, right? Just the order is different, right? Because you know that this will get printed in between this and this. So this should be there. If I revert it by 90 degree like this right subtree node should be there at the bottom, so it should be pushed first, and then this root with its flag changed to 1, and then left subtree node. Both of them should have that flag, the flag as 0, 0 each. So when you see this happen, you check, is there a right subtree? Yes. So you push this with the flag 0, and now you push this with the flag 1. And then when you push this, you push your left subtree in the end, you push it with this flag 0. So you keep doing this thing on and on and on, and this is how your job would get done. So the only thing that would change is that here you have pushed your right subtree, here you have pushed your left subtree, okay? Now this particular thing that you have, so this has to come in between here. That is the only thing which would change, and I don't think anything else has to change. Now what are your thoughts on post order? Can you do post order also? What will be the only difference in post order? I think the only difference will be that now this thing will come at the top, not here. Because now first you would want that whatever is my root, that must be printed in the end. So that root itself has to be pushed with the flag of 1. And then before this root, so I have this root 1. And before this root, I would want my right subtree to be printed. And before that, left subtree to be printed. So after printing my root, I will push my right subtree node with this 0, and then left subtree node with 2, 0. So this is how it would go on and on. So you print your left subtree, which is starting from root, and then you would print your right subtree, and then you would print this thing. So you will be able to do that, right? And all these time complexities and space complexity as well are order n, right? Space complexity is order 2n actually. In fact, not 2n, order 2h. And the reason behind that is because you are pushing a pair. Apart from the node, you also have another variable. So you have to take into consideration that also. So if the size of the stack was order h, the number of elements in exact terms were order 2 into h. Does that make sense to everyone, guys? Yes or no? Notice one thing on the board, that the order here is just reverse of the order that was there for recursive traversals. Yes or no? In recursive traversal of preorder, first you did something for root. But in the iterative traversal of preorder, whatever is being done for the root is being done in the end. It's easy to see, right? That has to happen, right? Why that has to happen? Because if you want something to be executed first, that should be pushed last in the stack. So if you get this thing, you get it all. So all of us understood this generic approach, and all of us realized that it can be easily modified as per our wish to perform Inorder, Preorder, or Postorder, Traversal, whatsoever it is. Now I want you guys to take a look here, and some of you were already giving that solution, but can others also think of it now that, hey, if I ask you for just preorder, can you get your job done for preorder traversal without having to use this flag? So in the approach itself, that is very, very clear. I'll tell you why that is very, very clear. The reason behind that is, let's say you started your journey with this one, okay, or let's say whatsoever you can think was there at the top of the stack, okay. Let's say this 2 was there at the top of the stack somewhere, okay. Let's say this 2 was there at the top of the stack with 0, with its children not pushed. Now whatever is there at the top of the stack, you take that out, and after taking that out, what do? You push its children in the proper order. So you took it out and you pushed 4, 0 because that was the right child, and then you pushed the left child, and after that you push this 2 back again with this 1. You know for sure that if something was there at the top of the stack, this 2 was there at the top of the stack at time t dash, and now it is there at time t dash plus 1. So whatever was there at the top of the stack, after insertion of its children in the proper manner, that will again come at the top of the stack with 1, and then that will get popped out. It will happen for any damn node that had a flag of 0. So I can simply say that, hey, why am I even doing that? I mean, if let's say there is something which is at the top of the stack, I'll erase it again. If let's say this is there at my top somewhere, okay, then let me just take it out. I don't need this thing. Let me just take it out. And after taking it out, I'll push its children in the proper manner, which is 4 and then 3. And then I'll simply print it. I don't need to, keep a track of whether it is seen or not, because the moment I see it, what preorder does? Preorder first always prints the root, and then entire left, and then entire right. Okay. So because I have to print this thing first, print process will never come in between or never happen later. So what I can do is, the moment I see something is at the top of the stack, that means it is to be printed in that particular iteration. So let me just print it, and let me push its children in the proper manner, which is right first and then left first. And just keep iterating this thing as long as the stack is not over. So this way also you can get your job done. Again, now it becomes very, very simple. Like now you'll just have a stack of nodes, node star, we call it S, and while stack is not empty, just writing the pseudocode because that is written, so don't want to write it again. The first thing that you do is you take that element from the stack. Let's say that element is n, node star n, and then you pop it. And the first thing that you do is, if you push the left child if it exists, first push the right child if it exists, and then push the left child if it exists. And after you have pushed the right child, after you have pushed the left child, why push it again? Because it will be printed, right? So then simply print that root value. That's it. And this thing can go on, and your preorder traversal would be done. So in preorder, it was very easy for me. Why? Because printing process is the first thing that I have to do. So let me do that right away. Okay, take it out, and then whatever is to be done in future, push that, and then why push it again? Just do it and get rid of it. But can this thing be used up in other forms of traversals? Can I use this in Inorder traversal or Postorder traversal? No, because there the printing process will happen in future. So let's say you talk about post-order traversal, printing process will happen once this and this is done. Similarly, in order traversal, printing process will be done after this but before this. So it can't be done like that there. So let's move on from pre-order to in-order. And what we are trying to do, guys? We are trying to perform in-order traversal using iterative approach without this flag. Then my extra space will be proper order of h, right? Then I don't have to, where h is the number of nodes and space acquired by every node is, let's assume that to be constant whatsoever. So can somebody suggest me how to get the job done for in order without this flag? Think of it in this manner. You see there is a tree on the board, right? There is already a tree, this one. Let me draw a neat tree. Yeah, I have drawn it big enough to try to confuse you. Let's say you get confused or not. Which will be the first node to be printed here in this tree? 6, right? So can I, generalize it to something like this, that hey, if the tree is given to me, then if I take the path root left, and then wherever I reach, so the first such node in this skewed direction such that that node doesn't have a left child will be the first node to get printed. And why will that happen? Because if a node is getting printed in my in-order traversal for the first time, now look at it very carefully. See, the pattern of in-order is first left subtree, then a node, and then the right subtree of that node. So if let's say there is a node that is getting printed first, now this node would also be root of some subtree, right? This node will also be root of some subtree. Now if it is getting printed first, that means its left subtree was null. Only if the left subtree was null, the left subtree did not get printed and the node got printed. And then after this, its right subtree would be printed. So it is common sense to say that, hey, the first such node, because the first thing that you do is you call for your left and you go on and on. So the first such node in this path which will not have a left child will be the leftmost node in this. Leftmost node could be something else also if it goes like this. So don't say it is leftmost node. It is that node which falls in this path at the end. That would be the first node which would be printed. Does it make sense to everyone, guys? Is everyone clear with this? Because this is the basis of solutioning. Now tell me one thing. In this tree, what will be printed after 6? 16. After 6, 16 will be printed. You are saying after 6, 16 will be printed. Agreed. Now tell me one thing. Let's say if this did not exist. This did not exist, guys. Don't look at this. Its right child was null. In that case, after 6, what would have got printed? 2 would have got printed, which is the parent of 6. So what did you observe here, guys? See, when this was connected, so let's come back. Now it is connected, okay? Now it is connected. So when a particular node got printed, it got printed because there must have been a recursive function call that would have been made for this node, correct? Yes or no? Now, because this node did not have a left child, so nothing got printed in the left, this node first got printed, right? And then two things can happen. Either it has a right subtree or it does not have a right subtree. So if it has a right subtree, then the function call would be made for that right subtree, correct? And only once that is done, once it is over, then it means that, hey, for this f of 6, which is here, the left was null, the right was something f of 14. So you printed 6 and then you did f of 14, and now once this is over, you will come back to the parent, which is f of 2. So it is important to remember this 2. Similarly, for this 2, when let's say this entire thing is printed, when this got printed here, and then this 2 got printed, and when this f of 3 got printed, you want to fall back to that 1. So it is important to remember your parent. Who was your parent? Because that parent is the one who called you first. And now once you get over, you should get your parent the opportunity to print it and print its right subtree. So it is important to remember your parent somewhere. So if you realize this, then your job becomes very easy. So if it is important for me to remember this parent, One way in which I can touch this node is by doing root, root left, root left, root left. But when I reach here and do that, I will never be able to print anything in this part. Never be able to print anything in this part because I had forgotten that. So what should I do? While taking this journey, should I push these nodes in a stack? Because if you push these nodes in a stack, then it will ensure that you have your parents there with you in the stack. So all that I said was, while undertaking this journey, keep pushing the nodes in the stack. If you do that, then you will see that your stack will have a 1 in it, and then after 1, when you come here, you will push 2 in it, and then you will push 6 in it, right? So initialize your stack with this particular path in this manner. Once you do that, then you know for sure that, hey, whatever is at the top, that is the thing which is to be printed first, okay? Because it is the first node in this path which did not have a left child. That is the reason it became top. So the first thing you can do is silently print it, pop it and print it. And then what are the cases that are possible? Tell me. There are 2 cases. First case is that it has a right subtree, and second case is that it does not have a right subtree. Let's say it does not have a right subtree. If it does not have a right subtree, what will happen? It means that the job of the subtree rooted here is done. So now the control should go back to the parent. So in that case, I don't have to do anything. If the node to be printed does not have a right subtree, simply print it and that's it. Nothing else to be done. Automatically, the top of the stack will be its parent now, which will get printed. So what was my first case? So whatever cases I am writing, that is with respect to whatsoever is the top of the stack. So if no right subtree, if right subtree does not exist, don't do anything. Don't do anything, right? Yeah. If there is no right subtree, nothing is to be done. But if there is a right subtree, that means that this node is printed, and once a node is printed, I know that after printing a node, before you print its left, and after printing a node, you recurse on the right subtree, correct? Now recursing on the right subtree means that now again this thing should be printed the way this was being printed, right? So this thing should also be printed in the in that particular in order manner, right? So can somebody suggest me what to do in the second case? If there is a right subtree, what should I ideally do? Any suggestions? Push the right left until not null. That is what you do whenever you embark on a particular tree or subtree. You always first push the leftmost node. So now again you have to, so if there is a right subtree, then take this path and just push this entire path again. Let's say it had a 20 here. Okay. So you'll push this entire path again. So now you'll have 14, 15 and 16, right? Now again, what is the top of the stack? That is 16. So now you will print this 16. Does this 16 have a right child? No. Okay, so you won't do anything. Next iteration, automatically its parent becomes the top. You print this parent also. Does this parent have a right child? No, nothing to be done. Now you come back to this 14. Do you see that because you had stored this path, the moment you came back from 16 to its parent and from 16 to its grandparent, because the parent was there, now you can go to the right subtree. Okay. So again, first thing that you would do is you would print this 14, and that is the right thing that you are doing, right? Because now you have printed entire left. So now you print this node, and now you would print the entire right subtree. So again, when the right subtree exists, if let's say this chain was like this, you would have pushed this entire chain. So if there is a right subtree, you push that entire chain again. And if there is no right subtree, you do not do anything, you automatically fall back to your parent. So you see how things happen here, right? Because if the right subtree does not exist and you have printed a node, what does it mean? I repeat it again. If a right subtree does not exist and you have printed a node, so that means the reason you have printed a node is because you have already printed the left subtree. Now if right subtree does not exist, nothing to be done. Simply fall back to your parent. Don't do anything, automatically you will fall back to your parent. And if the right subtree exists, then again in the right subtree you have to print the entire left chain. Okay? And this is how this thing will keep on going and going and going, right? So how is the implementation going to look like? So first thing that you have to do is, so you will have a temp pointer initialized to root, and first this chain is to be printed. So while temp is not null, you will keep on doing stack dot push temp, and you will do temp equals to temp left. So this way your stack is initialized. Now you can have your logic run. So while not of stack dot empty, okay, till that time you have to do few things. What are those few things that you have to do? Whatever is the top of the stack, you know, the top of the stack is the leftmost node of any subtree, So first thing that you would do would be you would print the top of stack. Okay, so first pop it, first top, then pop, and then print the top of the stack, and then after it, if right subtree doesn't exist, simply continue. Else, you know what to do. Else this entire thing has to come over here. Else you will push that entire chain of the right subtree. To do that, you will take a node n, which will be whatsoever was your top pointer. Let's say that was n1. If that was n1, you will do n1 right, and then with this n you will write the same code. So while n is not null, stack dot push this, and then keep changing them. So this entire thing will be written here for this n. And then again this will go on, and this is how your job would get done. Does it make sense? Does the pseudo code give you an idea how to write the code? Again, what is the time complexity here? So it's very easy to say time complexity is now, right? Any node is being inserted once and expelled once, right? So it will be 2n again. Extra space, if you realize, that will also be order n. Okay, and here, because I'm not using, in fact, you should not say order n, you should say order h, because it will be order n when it is a skewed tree, right? So always say order h, that is more generic, because you know, it would never ever happen that the number of nodes that you have are more than the height, because anytime you are considering a particular route to leaf path only, or a particular route to some node path. Okay, it never happens that you have nodes of that path also. It's just one path. So whatever is that longest path, that would correspond to my space complexity. So did you guys realize it, that how I can perform in order? And so what did we learn? First we learned recursive ways to perform all the 3 traversals, and then we learned a generic iterative way for all of them. The problem with generic iterative way was that I was using that extra flag thing which some interviewers might not be happy with, so that they might ask me to do it without that. So preorder was very easy, and inorder also, after taking that observation, after looking at this pattern, okay, became very easy. So first the leftmost node, and then after the node, if right subtree exists, again the leftmost, and if it does not exist, fall back to the parent. Store the parents in your stack in the order of traversal. Okay, now remains post order. So can you do post order without that count? You know, post order is a bit tricky without that count. Can you guys try on your own once post order without the count? Okay, so take a try. Okay, it will be very, very interesting.